Welcome to another module in this massive open online course. So, in this module we are going to start looking at a new topic, that is conversion of analog signals into digital signals, alright. And the first step to convert an analog signal to a digital signal, one has to make the signal discrete in time, alright. So, we have to sample the signal, alright. So, we are going to start looking at sampling to convert analog to a digital signal, okay. So, we are going to start looking at analog to digital conversion, all right, to convert an analog signal to a discrete signal, and the first step towards this is sampling, okay. And what does sampling do? Sampling converts, so sampling is the first step in analog to digital conversion. This is the first step in analog to digital conversion. And what does sampling do? Sampling converts a continuous time signal into a discrete time signal, okay. So, sampling, the basic idea behind sampling is to convert a continuous time signal to a continuous time signal to a discrete time signal, okay. For instance, let us say we have our signal, let us draw a simple signal here to illustrate this point. So, we have this signal, all right, which is a continuous time signal. Now, I want to sample it, all right. So, I am going to sample it at certain specific discrete time instance, which are also known as the sampling instance. So, let us say this sampling frequency, or let us say this sampling time is 0, then I sample it at Ts, second sample at 2 Ts, 3 Ts and so on, then minus Ts, minus 2 Ts. So, this is my signal, let us say MT, and these are the samples of the signal, okay. These are the samples of the signal, and you can see that the samples of the signal are extracted at every Ts or multiples of Ts. This quantity Ts is basically the sampling interval, all right. So, once every sampling interval we extract a sample of the signal MT, that is the signal to be sampled, okay. So, we have our signal, so we are extracting one sample every Ts. So, your Ts equals the sampling interval, okay. This quantity Ts is a sampling interval, and you can say this is a periodic process, it is repetitive, that is after every Ts you extract a sample. So, minus 2s, minus 2 Ts, minus Ts, 0, Ts 2. So, at every multiple of Ts you are extracting a sample. This is periodic, repeats once every Ts. So, Ts is the sampling interval, that is a period of sampling, and 1 over Ts is the sampling frequency, alright. So, correspondingly, since this is a periodic process, sampling frequency, which we will see is a fundamental quantity of this sampling process, Fs equals 1 over Ts. So, your sampling frequency is Fx, sampling interval is Ts, and therefore, sampling frequency Fs is 1 over the sampling duration or the sampling interval Ts, and therefore, this is basically you are sampling this at sampling frequency when you are extracting, since you are extracting samples once every interval of duration Ts, alright, the sampling interval is Ts, the sampling frequency is 1 over Ts, which is denoted by Fs. And naturally, the sampling process can be represented as follows. So, I take my signal again, okay. This is my MT, this is my continuous, this is my analog signal. I can multiply it by an impulse train. Now, what I am going to do? I am going to take an impulse train. Okay. So, this is my impulses which are spaced so, I can take the product of this with this, which is my impulse train. Now, if you look at this, this has an impulse at 0, for instance, this is an impulse at 0, Ts, 2 Ts and so on, minus Ts. So, this is an impulse train, is a train of impulses which has one impulse, that is it is a periodic signal of impulses with period Ts. So, this is a periodic signal of impulses. Periodic signal of impulses with period, that is you have basically one impulse every Ts. So, when you multiply this impulse train with the signal, what you can see is each impulse at the point of that impulse, for instance, impulse at 0 will pick the magnitude, will pick the level of the function of the signal at 0, impulse at Ts will pick the level of the signal at Ts, and therefore, they are creating basically a modulated train of impulses. The height of each impulse, once you multiply the impulse train with the signal, the height of each impulse or basically the scaling of each impulse will be proportional to the signal level at that particular time of that impulse, alright. So, one way to sample is basically by multiplying the original signal to be sampled with an impulse train. This is also known as ideal sampling or impulse sampling. This is also multiplying this by a train of impulses, this is also known as ideal sampling, okay. Ideally, we want to multiply it by a train of impulses, okay. Now, let us characterize this impulse train of impulses. We have an impulse at we have the impulse train. Let us look at the impulse train. If you look at this impulse train, we have impulses at, well, you have impulses once every Ts. So, you have impulses at 0, impulses at Ts, impulses at 2 Ts, so on, and you also have impulse at minus Ts, minus 2 Ts and so on. And therefore, if you look at the corresponding signal, that is going to be impulse, well, impulse at 0 delta t plus impulse at Ts delta t shifted by Ts, this is impulse shifted this is your impulse shifted plus delta t minus 2 Ts. plus also impulses at minus Ts, that is delta t plus Ts, and this is continuous so on delta t plus 2 Ts, and it is continuous so on. And therefore, if you look at this signal train of impulses, this can be represented as summation n equal to minus infinity to infinity delta t minus n Ts. This is basically your impulse. This is basically your impulse train, that is basically you have this sequence of impulses, one impulse at every Ts or multiple of Ts, that is impulse at 0, Ts, 2 Ts, so on, impulse at minus Ts, minus 2 Ts, so on. So, each impulse shifted is at n Ts, where n can be any integer 0, positive, negative. Each impulse shifted to n Ts is delta t minus n Ts. Your summation, you are considering the summation of all these impulses from n equal to minus infinity to n equal to plus infinity. This is your impulse train. Let us denote this by g delta of t. This is your impulse train, g delta of t. Okay. And now the sampled signal, as we are saying, the sampled signal now the sampled signal can be generated, this is your mt into d delta t, that is product of original signal. This is your original signal, signal to be sampled, and g delta t is your impulse train, which is mt times summation n equal to minus infinity to infinity delta t minus n Ts, which is equal to summation n equal to minus infinity to infinity mt delta t minus n Ts. Now, you can see mt into delta t minus, now you can use the property that mt into delta t minus Ts is equal to m of n Ts into delta t minus n Ts, where we are using the property mt into delta t minus t naught equals basically m t naught into delta t minus t naught. That is, when you multiply a signal by impulse shifted to t naught, then it simply picks the value of the signal at t naught. Alright, that is how we are basically sampling this signal, right. So, we are able to extract at each n Ts, we are able to extract the sample or the level of the signal at n Ts, that is your m of n Ts, okay. And therefore, this gives us n equal to minus infinity to infinity m of n Ts delta t minus n Ts. This is your m delta, this is your m delta t. Okay, this is basically your sampled signal. Okay. So, your sampled signal is summation n equal to minus infinity to infinity m of n Ts into delta t minus n Ts, and what we are doing is basically very clear. We have this original signal, alright, which is varying with time, and now you have this impulse train, you have this train of impulses at T at 0, Ts, 2 Ts, 3 Ts and so on, similarly minus Ts, minus 2 Ts, so on. So, you have this impulse train which is at 0, Ts, 2 Ts, 3 Ts, minus Ts, minus 2 Ts. So, you take the product, basically what you do, what you are doing is you are taking the product of the original signal with this impulse train, and therefore, what you have is basically the signal at 0 will pick m of 0. So, you will have basically you will have signal at 0 picking this value corresponding to this is your m of 0. So, at 0 you will basically pick m of 0. At Ts you will pick m of Ts. At 2 Ts you will pick m of, well, whatever is the value here, that will be your m of 2 Ts, and of course, at minus Ts you will pick this value, that is your m of minus Ts. At m of 2 T, at minus 2 Ts you will pick m of okay. So, this is basically your sampled signal. Okay. Which is basically again your sequence of impulses. This is basically your sequence of impulses. This is your sequence of impulses with the amplitude of the impulse, correct? The amplitude or each sequence of impulses with which are scaled proportional, which are scaled by the message signal value of the message signal at the sampling instant, at each sampling, which are scaled by the message signal value at each sampling instant. So, we have this sampled signal, okay, that is your m delta, and that is the expression that is given by this expression. Remember, m delta t equals summation n equal to minus infinity to infinity m of n T s delta t minus n T s. This is your this is the sampled signal that we obtain. Okay. So, this is basically the sampled signal that we obtain. And now, we what do we want to do? We want to look at the Fourier transform, we want to look at this behavior of this in the Fourier domain. So, we want to look at the Fourier transform. We want to look at the Fourier transform of the sampled signal, that is, what is the Fourier transform m delta f of the sampled signal and how is it related to m of f. Where m of f is a spectrum of the original signal, all right. Remember, m of f m of f is the spectrum of the original message signal mt, that is m of f is the Fourier transform of mt, all right. So, we know the spectrum of the original signal, all right, m of f, that is m of t is the original message signal, its spectrum is m of f. We know that we are sampling it with an impulse train at sampling frequency fs, that is sampling interval Ts, all right. Let us say this is sampled with the sampling frequency is Fs, sampling interval equals 1 over Fs, that is equal to Ts. Now, we get m delta t, which is your sampled signal, How is the Fourier transform of m delta t? That is, if we call the Fourier transform of this as your m delta f, how is it related to m of f? Alright, what is the relation in the, what is the relation of the spectrum of m delta f to m of f? And remember also, more importantly, when we are sampling, we are losing the information, because we are only extracting the information of the symbols or the signal, original signal at the sampling instance, that is multiples of Ts, 0 Ts, 2 Ts, minus 2 Ts, so on. So, we are losing the information contained in the signal in the intermittent duration, alright, in the intervening duration, that is, we are losing the information corresponding to the interval 0 to Ts, alright, the information in that particular interval, alright, and that leads to distortion, alright, that can lead to distortion. Alright. So, we are going to see when does that lead to distortion and what kind of distortion. So, basically if you look at, go back and look here, you can see that basically we are losing information in sampling. We are losing information because we are extracting only the information at the sampling instance. So, we are losing information. This can cause to distortion, which means this can lead to distortion. Alright, it can lead to distortion. If you are not able to recover all the information from the signal, that is, information has been lost, then this can lead to distortion. Alright. So, we want to see under what conditions, what is the type of distortion, and under what conditions, that is, how can we fix the nature of sampling such that the distortion is minimized, and if possible there is no distortion at all. Right, how to fix the parameters of the sampling to minimize distortion or possibly no distortion. So, the question we want to answer is how to fix the parameters of sampling sampling parameters to minimize or if possible avoid distortion. Either we would like to, well, ideally we would like to avoid distortion, correct. Ideally we would like to avoid distortion, but if avoiding distortion, that is making distortion completely 0 is not possible, then at least we would like to minimize the distortion that is caused by loss of information which is arising due to the sampling process. Right. So, these are some of the questions that we want to answer while sampling, while considering the sampling of this analog signal, which we will consider in the subsequent modules. Thank you very much.